First of all,
In
to
this lab, we
understand
build
how
a mariotte
fluid
bottle.
systems work, it
To
is important
study
to know the
steady
basic
flow
principle
under
under
constant
constant
pressure,
pressure, applying Mariotte's law.
we focus on three key
Also,
concepts. The
we
first one
analyze the
was
flow
Mariotte's
using
law,
Bernoulli's
which relate
principle
pressure
and
and volume
Torricelli's
in
law
gases
to
at
understand how
constant
pressure,
temperature.
volume, and
The second
velocity
one was
interact.
the Bernoulli's
In
principle,
this lab, we build a Mariotte
which
bottle
connect
to
pressure,
study
velocity, and
steady
height
flow
in a
under
fluid.
constant pressure,
And the last one
applying
was
Mariotte's law.
Torricelli's law, which
Also,
describes how
we
fluid
analyze the
it
flow
depends on the
using
height from
Bernoulli's
which it
principle
is
and
falls.
Torricelli's law to
This links
understand how
gravity and
pressure,
Okay,
pressure.
so talking about laws and principles, we have three: the Bernoulli's law, the Mariotte bottle, and the Torricelli's law. The Bernoulli's principle states a relationship between the pressure, density, velocity, height, and the gravity, and states that pressure plus density by the height by the gravity plus 1/2 of the density by velocity square is equals to a constant. This could be proven by the Mariotte's bottle, that the Mariotte's bottle is a bottle which has a straw here, like in the bottom, to keep the water flowing outside, and also a straw in the top of the cap, so that air flow is constant. In the Mariotte bottle, the flow is constant due to its constant pressure. And then the third concept or law that we will be seeing is the Torricelli's law. That the Torricelli's law states that in a bottle, which has also a hole for the water to flow, the velocity in which the water is exiting is proportional to the height where the liquid is. And also states that, for example, if you have like a bottle, like it's, I don't know, it's like this, and the water level, or the liquid level is at 20 centimeters, the velocity would be the same exiting the bottle than it would be the same if you drop the liquid from here to the
To
ground.
make the Mariotte bottle, we use a plastic bottle, a small straw, a large straw, a knife, a silicone gun, silicone bars, and a lighter. First, we use the knife with the lighter to make a hole in the bottle cup, the same size as the large straw. We seal it with silicone to prevent leaks. Then, at the bottom of the bottle, we make another hole, like the size of the small straw. We insert it, and then we seal it with silicone for the same to prevent a leak. And this is how we made our Marriotte's bottle.
Okay, so and for the experimentation, we used like 3 steps. First of all, was building the bottle, then was recording of the five trials with using the Marriott's bottle, and finally the tracker analysis, which here we have a screenshot of a tracker window where we used a flexometer as a reference, and there are the charts and the white points regarding the T of time. For the results, I would like to start with the theoretical framework, which we have 4 formulas that we would be using for calculating all the theoretical and the experimental results. First of all will be the Bernoulli that you can see from point 1 to point 2. We would clear the velocity 2, and we could eliminate pressure 1 and pressure 2 since it's the same, velocity 1 since it's 0, and we would basically just clear, so it would give us that result. For the second one would be Torricelli's. The third one would be cross-sectional area to calculate the area where the water is living out below the bottle, and the flow rate, that would be Q equals the cross-sectional area by the velocity of, depending on the law or principle that we're using. So for this, for the theoretical results, we use the laws and formulas explained before, and with the data that we collected, that would be the initial water height from the straw from where we're starting the experiment would be 11 centimeters. The difference between the straw that it's like in the horizontal way and the vertical and the horizontal, that would be 6.5 centimeters, and the diameter of the straw, that would be 0.5 centimeters. With this, we could calculate, with the diameter, we calculate the cross-sectional area, and with the initial water height and difference between the straw, we calculated the velocity of Bernoulli. With the difference between the straws, we calculated the velocity of Torricelli. And with the velocity that we obtained from both, we substituted in the formula of the flow, and we obtained the flow of both theorems. Okay, for the experimental results, as said before, we use tracker to obtain or capture by in every moment the height of the water level in the bottle. Here we can see an example of the first trial of both moments. Of the first one would be the Bernoullis, and the second one would be the Torricellis. With the data collected by tracker, we use it to calculate the experimental results with the formulas explained in the theoretical framework. As calculated in the theoretical results, we use the same procedures just with different values given us by tracker. And finally, of the results, we have the margin of error. We use the formula that relates the theoretical and experimental values obtained. I didn't put the calculations in because they would be a little too much, but after we calculated every percentage of error regarding the Bernoulli flow and Torricelli's law, we made the mean error of the 5 trials regarding each theorem, and for the Bernoulli we got 7.56, and for the Torricelli's we got 11.07 percentage. And I would like to state that, for example, in the results, we could also see that for the Torricelli's law, the velocity was higher than the Bernoulli's, and that could be seen on the videos that were made during the trials and also in the tracker.
For the discussion of results, we can both see Torricelli's and Bernoulli's laws in this experimentation. Torricelli's law by taking into account ideal conditions like no pressure or no resistance, and Bernoulli by taking into account for pressure head. In our specific results, both theoretical and experimental, we can see some error margins that deviate from one model to another. For Bernoulli, we have an error percentage of 7.56, and for Torricelli's, we have 11.07. This indicates that while the large straw was still submerged in water, Bernoulli's model approximates better how the velocity of the stream works and how the flow rate goes while having a constant pressure. And Torricelli's indicates a better approximation for when the water reaches the end of the large straw, and how this velocity changes and reduces with relation to the level of the water. For our 5 trials, we have some discrepancies between this analysis, and we have to take into account some systematic errors or random that we could have been responsible for. For example, some imperfections between ourselves and the construction of the device, like seal imperfections or that the bottle wasn't rigid enough. Also, we can take into account the environmental context, like maybe our lab had a strong wind current, or that we made some human manipulations that deviate the data results. Also, the tracker software, because this has some sensitivity relating calibration and the quality of the video, so all of this could have affected the data we obtained from this software and how we analyze it later on. But overall, we can see that from our experimentation, both models are validated and that in their respective contexts, both are proven.
Conclusion. So after conducting our mariotte bottle experiment, We closely analyzed how the water flowed and compared our measurements to the theoretical expectation using Bernoulli and Torricelli's equations. The accepted value of gravity, 9.81 meters per second squared, was key for our calculations. Our results showed average margin errors of about 7.6% for Bernoulli's equation and around 11% for Torricelli's equation. And our experimental values for gravity were quite close to the standard. However, we encountered some practical issues that affected our accuracy. The biggest problem was water leakage around the bottom straw. At first, we tried sealing it with modeling clay, but it didn't work because after several uses, the leakage increased. So we reinforced the modeling clay with hot silicone, which helped reduce the leakages, but they didn't stop. So another limitation was that our bottle had irregularities and it wasn't a perfect cylinder. So our measurements of water levels and volume were less precise. So to improve future experiments, we recommend using better seeding methods like using rubber grommets or aquarium grade silicone to really minimize leaks, and also changing the bottle so it is more like a perfect cylinder. So in summary, the differences between our experimental and theoretical results were likely due to these equipment issues, as well as some limitation of the equations used and our measurement methods, like using tracker video analysis. Thank you for your attention.